Hello everyone, my name is Patrick, I work at Wooga, and today I will talk about a few systems that we built for our games, the databases that we use, the mistakes that we made, and how we got out of it. But first, let me ask you a question. Do you like to play? Because I think we all do, because it's a natural thing, we learn things, we train, and we can also interact with each other. There's a big social component to playing where we learn to deal with other people, and it's also good for us to deal with other people or animals, for instance. And that's what we do here at Wooga. We do social games and casual games. So we target users that normally don't play video games. For instance, like my mother, she loves to play one of our games. And those games are, for instance, like Monster World, where you have your own beautiful garden, and you can help your friends and visit their garden and help them watering their plants. Or Diamond Dash, which is our most successful title, where we have a few gems on the iPhone or iPad, and then you have to click. The colors that are the same, they disappear, new ones come. You play that for 60 seconds and try to beat the high scores of your friends. So now get to the technical part of it. Those games, they provide some challenges for us. To give you a context of the numbers that I'm talking about is monthly active users for Diamond Dash. So that's the number of users that play that game played that game in the last 30 days. And that's the number of users that played that game yesterday. So what does that mean in terms of more our kind of thing is requests per second. So that boiled down to 6,500 requests per second for the game Monster World that came in through the back end. That might not be a big deal in general, but in our use case, it's a problem for the database. And the reason why that is, it's write heavy, which means pretty much all the requests, or let's just say the majority of requests that come in, need to write to the database. So our biggest problem is scaling out the writes to make the database work with that. And we have done so in several iterations over several different games. We try to evolve with our architecture to make that work. And to give you an idea how, in case you didn't know, how the classic setup works for us is we have one user that plays, goes to Facebook on a desktop, clicks on a game, and it loads up the Flash client that talks to our game backend and also talks to our reporting backend, which is important for the business analysts. So they can do some data with it, improve the games, run A/B tests, stuff like that. The same we have for iOS games as well. So the first two games that they've built, that was actually before my time, were Brain Buddies and Bubble Island. And they ran on LAMP. Well, actually not exactly I think they used Nginx, but LAMP is a bit hard to pronounce. So the bottom line was MySQL does scale. If you looked at the numbers before from Diamond Dash, that thing actually still runs on MySQL, and it runs nicely. So I say for certain use cases, it definitely scales if you have the right people. If you have an engineer that sets up the machine correctly, that gives you fast machines and configures them in a way that they'll fly, and if you have engineers that write smart queries and think about how they insert data and how they query data without killing the database. Now moving on to another game, the next game, Monster World. They decided to build this one on EC2 in the cloud in order to be able to handle big spikes in traffic, because on Facebook it can happen that all of a sudden your game goes through the roof. And they used Rails instead of PHP, but MySQL was still there. And this is this fairly standard setup that we have. They started out with MySQL, but sharded initially because they knew they had to shard eventually, so they wanted to do it early on so they get that technical problem out of the way. So there's a big story about how this game scaled and what the problems were. And our lead engineer, Jesper, has a great story, and I think he calls it 6 weeks in hell. And it has a lot of gory details of what exactly happened. But I'm just giving you the gist of it. they ran into through roadblocks. The first few were actually quite easy to manage, and they always found solutions to go around it. But eventually, they ended up with something like this. Now, imagine you have 2 or 3 people that need to run this thing and also write the backend code. So that's a classic DevOps thing we're talking about. So, and those 2 people have to write production code to advance in a game and make the game better, but also run this thing on EC2. And the next step is, so they had these 8 shards, and it wouldn't keep up with the writes. So what they started doing after that is, well, they don't know. They started thinking, well, the next logical step would be going from 8 to 16, but if you sum up the slaves as well, you end up with, what's that, 32 machines that you need to handle. And if one master goes out, you have to switch to the slave and come up with a new machine. So that's a lot of operational work. And so it turns out Monster World was a different use case. It was not an arcade game. So the lesson learned for me personally here is arcade games are not farming games like Monster World is. Consider the traffic and the backend and the databases. So they figured, well, this is not going to work if you want to spend some time actually coding apart from just dealing with operational hazards. So the light at the tunnel that they saw eventually was Redis. Because Redis is extremely fast. They had write problems, right? So needed to deal with writes. But it's also durable in some sense, not as extremely as MySQL, but you can have it persistent if you want. So what they started doing is they started moving the slow parts out of MySQL into Redis, especially the parts that, if you look at a farming game, you normally plant something. In Monsters is a monster garden, so you plant something, you're going to plot, you harvest it, you plant it like this cycle, and this is what caused the most traffic. So they moved that out to Redis, and then gradually moved out more and more that was hurting them, and this eventually saved the game Monster World in the back end, and so they could move on and start focusing more on other stuff. So the next game is the one that I actually worked on. It's called Happy Hospital. And from what I've learned from all the problems they had in the cloud and needing to have tons and tons of machines and having such huge operational overhead, we wanted to go dedicated. Because in my understanding, the cloud was just too slow for what it cost us. There was I/O was terrible, and the CPUs weren't the fastest ones, and it got expensive and expensive. But we wanted faster machines, as fast as we could get. The I/O should be fast, the network should be fast, so we don't have to deal with these terrible latencies between the application server and the database, because the higher the round trip is, the longer your eventual response time is going to get if you fire up more than one query, right? So we decided to go with Redis, and we came up with this. So the idea was have very few machines, but big machines, and just have everything as fast as we can. And we stored all the data instead of in a classic MySQL way of taking the user's data, and the users has, in Happy Hospital, you have room and you have patients. So instead of putting the patients all over here, and the rooms all over here, and the user here, but then we need to use the user's rooms. You have to go here through all the rooms and look down, and then you need the patient scroll down here. You would have one compound user. So you have Redis a key, the value is a Redis hash, and everything that belongs to one user is in there, which turned out to be really powerful because we could easily move that user around between environments, from staging to production and back and forth, which was extremely good for debugging, for testing, because you could just have a bunch of JSON files or YAML files that you just restored to your system, to your staging user, for instance, and see the world like the user that had a bug, right? And also in case of sharding, that's quite easy because you have to just shard by one key, and you don't have to shard all your models as well. And so we were fine. And the family was fine as well. But we ran into some roadblocks too, and those were the interesting ones. First of all, Redis started to do something weird. Because we would expect that the growth of memory to be linear to the growth of new users that came in, right? Every new user is a certain amount of memory, and it should grow linearly. It did that until a certain point, and all of a sudden then Redis memory growth just went through the roof. And we didn't really know what was happening, and we couldn't really reproduce it in a development or staging environment. It was just happening in production. So eventually, and we also figured out if you would restore a Redis dump into an empty Redis database, then it would consume much less memory than the actual production database did. So that started to become a problem because we were slowly running out of memory on our machines, which we thought would hold up for maybe half a year or a year. Another thing that tripped us is all of a sudden we had stalls in our system all the way through the stack. So on the top end, if you look at response times from your application, and all of a sudden it would just stall for 1 second, response times go up, and then cripple down again. And sometime later on, the same thing would happen. And we were looking at all the things and all the queues that were in there, and we couldn't figure out what it was until one of our engineers said, well, whatever it is, it has a clock. And it turns out it was periodic what was happening in those stalls. So as it turns out, there is a scenario in how Redis does the background save where the fork that it does can stall for up to 1 second. So this is what we were experiencing it was. And the problem was also we would run that on the master database, our background dump for backups, instead of the slave. So we moved it over to the slaves, and that problem was solved. But eventually, we could no longer do dumps. And first, the quick trick is always make sure that you check whether your offsite backups are actually working, and they're actually there, and they actually have a certain size in memory. So make sure that they are there, because for us, they just started disappearing. Luckily, we were monitoring them. So what happened? I think it was my misunderstanding of how copy and write works. Because I thought, well, Redis is forking a process, and then it uses copy and write to write out the dump of its data. So it never should reach a point where Redis uses twice the amount of memory that it is already using. I thought that would never happen. As it turns out, under a certain load, this is actually possible. So what happened to us is the operating system scheduler started killing that backup process before it was done writing. So that's actually the biggest roadblock we hit with that game. And it was terrible because now we had no backups and we had a master and a slave, but if anything happened to them, they were no longer persistent. If anything happened to them, we would lose all that data. So after I've done some crying, I was actually really sad about that. I wasn't even sure if I eventually get fired for a stunt like this because I think it was my fault. Anyways, I didn't get fired. And we came up with a solution that I call restore on demand. What we actually did is we started archiving the users because we figured a social game, you might have a lot of zombie users, as I call them. They start playing the game once and they never come back. But they still occupy space in your memory. And also users, they start playing for 20 minutes, then they don't play for a couple of hours, and then they come back and play again. But in the meantime, most of the time you don't need those users unless some of their friends is interacting with them. So what we do, we would archive all the users, and only when they started playing, we would load them from disk into Redis, then they would play there. So essentially, it's like a write-through cache. You can think of it that way. And after you're done playing, we write you to disk again. And that worked remarkably well, because instead of having millions and millions of users in your Redis database, you only need a few 100,000, basically, for the user that are actually playing concurrently, right? And eventually moved that to Disk Store, which is an experimental branch of Redis that never made it to production and is not officially supported, but we ended up using it, and it works really nice for us. We even wrote a version of it that instead of writing to disk, writes to S3, but we never tested that in production. So, moving on in the evolution of our games. The next one was called Magic Land, which was a medieval city builder kind of things. And the guy, Polo, who had designed that system, he worked previously on Monster World, and he decided to go stateful. And he had a great idea. That's, of course, a Captain Obvious statement. but essentially he wanted to get rid of the database in the sense we were using it. So he just said, well, we do it stateful, and we write to S3 in the backend. We write to S3 as our storage, and we run everything on EC2. So no database scaling and write issues, because if you are stateful, we can write to S3 sometime if you want to. We don't have to execute the writes all directly, right? We can bundle them up and send some state to S3. And he decided to build this in Erlang for various reasons. First, Erlang is well known for being excellent at distributed computing, excellent at concurrent computing, and it's really cheap in Erlang to get new processes, right? Because they're not system processes. So you can have thousands, 100,000, maybe even millions of processes in one Erlang machine. And if you look at that stateful context, you will see why that matters. Because let's look at how it would work on the backend if you start playing the game. You come to Facebook, you log in, the Flash client loads up, and it issues a login or setup call to a coordinator node, which assigns it a worker process or spawns one, which then acquires a log to make sure nobody else is writing to that user on S3 at that time. And then it loads that, fetches the data from S3, loads it into memory, and keeps it there. And from then on, the client keeps talking to that worker, and all the writes go directly there. And asynchronously in the background, we also write it to S3 so that we don't lose a lot of the data in case everything dies. And logout works basically in reverse. The session timed out in some way, the log gets released, and we write the user back to S3. And that is an excellent solution, and I think a remarkable one from those two guys that built that, because it uses very little servers on EC2, and it is stable, and it scales extremely well. I think at some point they managed to get the whole game through one application server. But it was just for bragging rights. They don't do this in production most of the time. So does everybody know what Facebook's Spartan project was? Okay. Facebook Spartan project. The way I understand it, it was essentially that Facebook wanted to push HTML5 mobile and wanted to create an app store on their iOS and Android applications. Right? So the only thing they could do this, of course, they had web views inside their iOS and Android applications where they could launch other apps and display them. So, and they wanted to have mobile games, that's why they partnered with us. So the idea was to write a mobile game, and we decided on an extension to Magical Land. That's called Magical Land Island. The problem there was the deadlines that was given, we were only 2 people. The deadline we were given was in weeks instead of months. So I started getting nervous, and they were talking huge numbers in expected traffic. They were saying, I don't know, it was in the millions on the first week, and I don't know, it was just huge. So after I was really confused, because here I am, we were 2 people, one a product manager, the other one is me. We need to build an HTML5 game on mobile, which is a feed by itself, but I also need to scale it and make sure it handles the traffic on a scale that was never seen in our company before. I ended up using Node.js because I thought, well, since I'm using it in the client already, and we probably will hire new JavaScript programmers to help us out, which we eventually did. We hired some great guys to pull that off. So I decided to do Node.js in the backend as well, so we can seamlessly switch back and forth. So that was settled. So I needed the database that requires very little operational effort, and that scales without sharding. So I don't have to deal with just, I add 1 more, I actually need to add 2 more to scale with the problem. And that has masterless replication. And yeah, so, and it could be, doesn't need to be the fastest kid on the block, because with JavaScript, we could write to the local storage, but we also could have asynchronous saving. So it was fine, it just had to be reliable, and Node.js is actually, since it's evented, quite fine with just sticking around and waiting for a database response. So I chose React. And that was good enough for that. I ran it on EC2, and I said, well, that's good enough for now. And as it turned out, it was good enough for good, because here's the kicker. The project never really took off in the scale that we thought it would be. So it went to an extent that it actually got stopped, and we released the game open source as a mobile. I think we changed the name. Yeah, we changed the name to Pocket Island. So it never really needed it. But anyways, through that operational time that I had with Riak, I have a few lessons that I've learned. First of all, I used Riak as a simple key value store. I didn't do any fancy with it. I didn't do any fancy data structure, or complex data structures, or complex queries that would come along with it. Essentially, I would store something like that. And so my experience in general with Riak is, I think it was a tank. It's fairly fast. It was actually a lot faster than I expected, and it's super robust. Like, little to no operational hazard. It was just fantastic, and it was exactly actually what they said it would be. So I was really happy about that. And the fact that you don't have a single point of failure in your database is just amazing, because I don't want to get up at 4 o'clock in the morning because the master just died. Now I need to switch to the slave and set up a new master and deal with this. With Riak, let's just say I had 5 nodes. If one node dies, I probably will just sleep through it and restore it in the morning. I'm going to be fine. Another learning is I use Bitcast as a storage engine, and that might not have been the best idea. But I never had to pay for it, because we never reached the amount of users that it would have become a problem. Because Bitcast, your keys need to fit in memory. And if you remember what I said earlier about a lot of zombie users that we have, and a lot of people that would just try out this HTML5 mobile game, oh, it's nice, and then they never come back. So there's a lot of users like that, and you keep them around in memory, as a key at least. So I thought eventually that would have become a problem. Lucky for me, it never did. And yes, this is an older version of Riak. I don't know if that's true for new versions of Riak. So what I wanted to do, I wanted to back up my system, and the first thing that I did is I would just do MapReduce over a whole bucket. Essentially what Riak did is it would go through all the keys. And remember, Riak is a distributed system, so you had to coordinate a lot and then return all those keys. And I almost killed the cluster like that, but I didn't, so I was lucky there. And this is a development problem, less than a production problem. But locally, especially on the Mac, your limit is fairly low, in the 200s. And Riak, when you say Riak start, it comes and says, well, you should adjust ulimit. And I was like, yeah, it's fine, because I kept thinking connections Riak can accept. I wasn't thinking file descriptors that Riak needs to write to, because I didn't think how LevelDB, for instance, works, that it has a lot of files, open files that it writes to all the time. So the problem was, even though it says you should increase your limit, it doesn't tell you that it didn't start. It just says, yeah, fine, but it's not saying I couldn't start on the standard out. You have to actually go through the log files to figure that one out. And here's my favorite story. So who in here actually has used Riak? All right, so actually, I think the story is new to you. And okay, so with Riak, you can attach to a node and get a shell, and you can you can call functions and change modules and change codes. Because it's Erlang. But what happened is how I normally get out of an Erlang shell is by typing Control-C twice. So what happens if you do this through a Riak attach shell is you just killed the node. And so I killed the whole staging cluster before I started to figure it out. I was already upgrading on production, and I think I killed 1 or 2 nodes until I figured it out. So yeah, that's the thing. So how am I doing? Okay. I wanted to go, yes, the next thing we started working on is Monster Mobile. Remember that farming game that I talked initially about it, that had scaling problems with MySQL, and eventually moved to Redis? So this time I had plenty of time on my hands to get this one right. So I thought, but well, up until now I think I'm still good. So I really looked into how other mobile games are doing this, because it was our first farming mobile title in that sense on iOS that we are working on. So I looked at other titles from Zynga and other competitors, how they're managing the protocol, how they deal with flaky connections, how they deal with clients being offline, how they deal with that you cannot have the same request pattern that a lot of the desktop clients have, where like every little action triggers a request to the server. Right? You can only do this with a broadband connection on 3G or lower. Just setting up an HTTP connection is quite expensive. You can't just go around and set up HTTP connections all the time. It's just not going to work. And also I looked at how cheating works, because normally on Facebook you would look at the backend and just validate everything on the backend, because you have a lot of control over there. And on iOS, you have a local disk and people can write to that. And so I looked at they would cheat, and it turns out they wouldn't attack the protocol, the cheaters, whose videos you would see on YouTube. They would attack the local storage and change configuration values and other funky things like that. Lesson learned for me was, first of all, an iOS client is not a Flash client. But I also learned that my Monsterville mobile game is not an arcade game, so I couldn't just copy and paste what our arcade mobile game was doing. So essentially I was asking myself that question. Do I need a database at all? I didn't want to go stateful because I didn't expect to have a lot of traffic, because here's the thing, on an iOS device you're in full control. So you have a local disk, so you can batch your updates in, let's say, once a minute, or go even higher depending on the demands of the game. So you don't, and essentially, so the database, what that means, the database doesn't need to be really fast. It can be fairly slow, it just needs to be extremely robust. But you can even take it a little bit further and say, well, let's just keep the backend simple and do not the staple thing, because it's wonderful, but it adds a little bit of complexity. Just keep it simple and stateless, and just write directly to S3, right? Just have Erlang or Node.js or whatever sitting as a thin layer on S3, and just reading and writing to S3 and make it check some stuff. So that thought definitely crossed my mind, and I'm not sure whether we're going to do this, but it's definitely a thought that crossed my mind. And also, I forgot the slide was there, sorry. The next question I came up with, do I even need a backend? So in an attempt to optimize myself out of a job, I could actually try something like this. And essentially have no database in that sense. For that I need to scale, no operational overhead, no backend I need to write, and just manage everything from the client in a smart way. At this point, I'm not sure if this is actually possible, but I will certainly look into that. And I think I finished really early today. Okay, that's all I got.